Hi everyone, welcome to the latest video in Omixon's Learn Me video series. My name is Adel Yuhosh and I'm going to take you through the short training video today. In this short video, I'm going to walk you through how to troubleshoot phasing ambiguities in HLA Twin Genotyping software. During analysis, the consensus genotyping algorithm of HLA Twin builds two consensus sequences, one for each allele for every locus of every sample. The variation between the two alleles allows the algorithm to distinguish one allele from the other. As long as the distance between the two variants is less than the size of the fragment from which the paired reads were sequenced, in practice this is approximately 900 base pairs for holotype HLA, the variants can be phased by HLA Twin, i.e. we can say with certainty that the variants are on the same chromosome or in phase. On occasion, there might not be sufficient information to phase all of the variants, usually due to long stretches of homozygosity between the two alleles. This is called cis-trans ambiguity or phasing ambiguity, and we will go through the specific cases and consequences of this phenomenon. In certain cases of phasing ambiguity does not cause an allele level ambiguity. We'll look at an example of this first. In this example we have lost phase, but the combinations of differently phased consensus fragments match only one allele pair in the database, so despite the phasing ambiguity there are no other matches. There is still a theoretical possibility that the consensus sequence combinations that didn't match anything in the database are novel alleles, and we have an ambiguous result, but in reality it is highly unlikely. To indicate this theoretical ambiguity, we show an info markup in the quality report. The other possibility is that the phasing ambiguity does lead to an allele level ambiguity. In this case, the generated consensus sequence combinations match more than one pair of alleles equally well. Usually a short list of ambiguous allele pairs is shown. It may still be possible to resolve this phasing ambiguity. The first thing to check is the distance between the heterozygous positions which are responsible for the phasing break. We can do so in the genome browser. And we need to note their distance, in this case it is 507. The library preparation is targeting fragments of 1000 to 1300 base pairs in size. However, these are substantially trimmed after the sequencing. The primers and the adapters are removed and sequences are also trimmed based on quality. The average fragment size will be about 450 base pairs, with a range of fragments smaller and larger than this, but with a maximum of around 1000 base pairs. If this distance between variants is less than 800 base pairs, then reanalyzing with more reads will most probably resolve the ambiguity, as it happened in the reanalysis of this sample, where I used 8000 reads to obtain more data from the sample. Note that if the average fragment size is smaller than expected, which will be marked with warnings in the quality control screen, there may not be enough fragments large enough to resolve the phase. Please note that processing more reads will result in higher noise, which might decrease the genotyping quality. When processing more reads, it is advised to use the original result and only keep the phasing information from the rerun analysis. The correct alleles, correct phasing can be assigned by hand. If the distance of heterozygous positions is greater than 800 base pairs, then processing more reads will probably not resolve the ambiguity. It can't be resolved with Illumina sequencing data gained with the holotype kit. I hope you found this short video useful. If you have any questions, contact us at support@omixon.com or place an inquiry with our sales team at sales@omixon.com. For more videos, please see the Omixon YouTube channel. See you next time.